I'm gonna start talking. So welcome everyone to Halifax, Nova Scotia, Canada. So we're so happy you made it to CHES. Hopefully you've enjoyed it so far. There's a lot more fun to go. I don't know where the clicker is. Can I do next slide, please? The talks, where the talks are located either here, next door, or downstairs. I'll wait for them to switch. Perfect. So you can see on the program, the location is written B3, B2 Argyle. So Argyle, take the escalators down twice. You're kind of at street level. It's where the tutorials were, is where the Argyle suite is. So it's all the rooms together is the third track. So the program chairs, I think I'll invite up to say a few words here. You want to say? While we're talking about the program, and then we'll switch back.
Thank you, Colin. I welcome everyone. It's very nice to finally see each other here in person. It has been a long journey, 1 year journey in CHES 2024, and we welcome you here in Canada.
Yes, so the plenary talks, and including the award talks and the invited talks will be here. It won't be streamed to other rooms. Anyway, so there's 2 invited talks and 101 contributed talks, and we hope everybody will enjoy it.
To know how busy the program chairs are, of course, if there's 101 talks times the average paper submission, you see how many papers you've had to go through. So thank you very much for a long year of effort. Some quick other notes. So the next slide, please. You got water bottles. There was water bottle filling stations on every floor. This one's across the hall over there, or not across the hall, across the way, sort of before the bathrooms. For the banquet and band, next slide, please. The banquet, keep your meal card ticket. That tells you which meal you'll get, and you'll just put it on your plate. So the dinner's in the venue dining room. There's a band at the Pacifico is the bar tonight. If you leave and come later, have your ID badge. There's security working the door. That's how they know who to let in. Next slide, please. There's several special rooms. So where the affiliated events were yesterday, those rooms, a few of them are open. So in particular, there's a prayer and meditation space, lactation space, and a breakout room in 503. So this room now has some round tables. If you're looking for somewhere you need to finish some work or anything like that, feel free to use that room. It'll be open for the rest of the time. The poster session on the next slide, please, is located right outside these doors. So it'll be right here. The poster, so you have a poster, find the poster chair, set it up Friday at lunch. The poster authors will have drink tickets. So please go and ask good questions to the poster presenters. And finally, next slide, please. The rump session notes. It's tomorrow night. There's still some time, and we have some quick announcements on that.
Yeah, this is just a reminder that the most important session is the rump session on Friday night. The call is on the website. Deadline is on Friday at 1 p.m. So please submit your rump session talks.
Yeah, we have surprises. So we look forward to interesting talks and hope to have a lot of fun. Thank you.
All right. Thank you, everyone. We go to the next slide, please. So thanks, everyone, for being here. Thanks the program chairs, the committee, everyone on the organizational side, and the sponsors who all made this possible. So there's a ton of people. There's some names on the boards outside and even more that we couldn't fit in. So we really thank everyone, tutorial presenters. Trying to think off the top of my head now, but I won't think of everyone, but there's a huge amount of people that made this possible. So we really say thank you to everyone who made it here, who made this, and we hope you really enjoy it. So with that, we leave it to you.
I think we will try to start as soon as possible and with the Slim, the first speaker. So we will now turn this to François, the first session chair.
Okay, hello everyone. So welcome to the first session. So now the first talk is talk enabling PERC and other MPC and DH signatures on resource constrained devices. And the talk is given by Slim.
So good morning, everyone. My name is Slim Bataib. I'm a researcher at TII. And today I will be presenting our work titled Enabling PERC and Other MPC in the Head Signatures on Resource Constrained Devices. So this is a joint work with my colleagues at TII, Loic, Alessandro, Marco, who is here, and Lucas. So let's begin with the broader context and goal, then dive to our methods and the result. So in 2022, NIST has launched an on-ramp competition to expand the selection of post-quantum signatures beyond the Lithium and Sphinx Plus and maybe Falcon. So By the end of the first round on June 2023, there were 40 schemes selected. So among the scheme, there is a category of schemes called schemes signature based on MPC in the head framework. These schemes are Biscuit, Mira, Mirith, MQ, On My Mind, Perk, Hide, SD in the head. Okay, let's focus on the implementation of these schemes on different platforms. So while the performance of these schemes on the x86 architecture are relatively well understood, there is a significant gap when it comes to their implementation in constrained platforms like the ARM Cortex-M4 devices. And so the goal of this research is to focus on the optimization, on optimize these schemes on such platforms. Okay, so the goal of this work is to optimize PERC for Cortex-M4 and other resource-constrained devices, and pave the way for enabling other MPC in the head signatures on similar constrained devices. Okay, because before we dive into details, let me summarize what we'll be covering in this talk. So I will start by presenting the MPC in the head signatures. Then I will discuss our streamlining techniques, followed by an overview of our results. And finally, I will conclude by the key takeaways and the future directions of this research. So at very high level, to build a signature scheme from the MPC in the head framework, there are 3 steps. So the first step is that I will build an MPC protocol that evaluates some one-way function f on some secret input, let's say x. Then I will use the MPC in the head framework to convert such function, such protocol into an interactive zero-knowledge proof of knowledge, evaluating if y, for example, is equal to f of my secret x. And the final step is that I will run the Fiat-Shamir transform on top of it to transform this identification scheme to a signature scheme. So I will quick reminder about these techniques for an MPC protocol. Let x be a secret that can be recomputed from n share x1 to xn. So an MPC protocol allows n parties, PIs, with input xi to jointly compute the function f of x for some function f. We require 2 security properties, correctness, which means that the protocol compute y is equal to f of x for some f, and the privacy, which means that PI do not learn anything about x beyond what can be learned from f of x. For the MPC in the head paradigm or transform, so the objective is to transform this MPC protocol into a protocol computing y is verifying zero knowledge proof of knowledge, verifying y equal f of x. So the main idea is that the prover P generates and commits to the share of x, then emulate in its head the MPC protocol, and reveals the view of n-1 parties. So here I describe the 3-round protocol, but identification scheme, let's say, but it can be 5, 7 rounds, depending on the schemes. So the prover will commit to these views, and the verifier will choose a random party alpha from 1 to n. And the prover will reveal the shares of all party except the party alpha and the output of alpha in the MPC protocol. And finally, the verifier V checks that the received views are consistent with the commitment and check the computations and the result of the MPC protocol. Okay, so now let's focus on our streamlining techniques, focused on optimizing the memory footprints of MPC in the head signatures. But before we dive into our technique, let's first understand what are the most memory-intensive operations in such protocols. So, as many of you may already have guessed, the most expensive part is the MPC, the computation relative to the MPC protocol. And this is not, this isn't surprising because such protocol involves the generation and manipulation of relatively, seed trees. These trees have n leaves, with big N is the number of parties in the MPC protocol. So the leaves of these trees are the seeds. These seeds are used in many steps of the protocol, and from them we derive the commitment. And so these seeds and commitments are saved in memory in the different step of the protocol. And there is a commitment that will be sent at the end by the prover, which remain unknown until the final step of the protocol. So we need to save all these commitment in memory. So this is what I described is what we do for one round. But since the soundness of such protocol is around 1/n, so we need to repeat this protocol many times to reduce the soundness to a negligible value. So we need to repeat this again and again. So it means that the seed trees and commitment persist in memory across all rounds. And actually, they are the primary factor influencing the stack usage. So in this slide, I will describe our streamlining techniques. There are two main techniques that can be applied for all MPC in the head signatures. And the first technique is that we will generate the seed trees, derive the necessary variables, and then promptly clear them from memory. And whenever we need the seeds or the commitment, we will regenerate them again. In the first technique also, we will absorb the commitment directly after their generation, so we don't need to save them in memory. So this absorption in the fly will contribute to the computation, for example, of the challenges in the scheme. And the second technique is mainly there is one commitment from the n commitment that is expensive to compute. So we will strategically save this commitment in memory. So this means that we have to save one commitment per each rounds, which not too much. And this is ensure efficient computation without overloading time complexity in each round. So let's dive in the details of the first technique. So as I said, we will use the seeds and then clear them in memory. For example, for the first part, you will use the seed, compute the commitment, then use the hashing API to absorb that commitment that will be used for the computation of the challenge. And then we will clear that commitment, generate the second seed, compute the commitment, absorb it, and we'll continue like this through all the leaves of the tree. And we will do this again for all rounds, starting from the first, the second, etc., to the last leaf of the tree. And the second technique basically is to cache in memory the most expensive commitment. Usually it's the first or the last, the first or the last commitment. So let's see how this, now let's see how this streamlining technique translate to concrete results. So for PERC, we obtain a streamlined scheme, signature scheme, which is compliant with the official implementation. It means that it passes the CAT tests and it runs for all the parameter sets of the scheme. And this reduced the memory requirement for any platform from 1,000 of kilobytes to about 85 kilobytes for security level 5 and around, I think, 32 kilobytes for the security level 1. And this is the first constant time implementation of PERC, compatible with the Cortex-M4 discovery board, and the first MPC in the head signature scheme for Cortex-M4, covering all the security all security levels. So this is the summary of results for PERC. Let's break down these results in detail for each platform. For the Cortex-M4 platform, we, as I said, we drastically reduced the memory footprint. For the signing algorithm reduction, we obtained a reduction of 15 to 14 times for the fast parameter and 47 to 70 times for short parameters. For the verification scheme reduction of 13 to 16 times for the fast parameter and 44 to 80 times for short parameters. On the x86 architecture, our streamlining technique comes with a trade-off, showing 60% performance degradation. What we can note here also is that our streamlined verification algorithm performs similarly to the reference algorithm due to a new optimization that we have introduced. Now I will present the result for other MPC in the head signatures. For biscuits, we reduced the stack usage of 13 to 16% for fast and 14 to 17% for short parameters. We noticed that the commitment recomputation for improved the stack usage more for biscuit than PERC. This is due to some parameter difference in the number of rounds and the number of parties in the MPC protocol. For MQ and MoMind, there are two parameter sets that are in the PQM4 project, which has a Cortex-M4 implementation. So we studied those, and using our technique, their memory footprint could be reduced by 6 to 14% for level 1 GF Gallowfield 31 fast and GF 251 fast. For the short parameter for security level 1, we show 19 to 48% improvement. For Mira and Wright, so we decided to analyze them together because they rely basically in the same MPC in the head protocol on Hypercube with the same number of rounds. So we faced some challenges to analyze them because they rely heavily on heap memory usage. So it's complicated evaluating streamlining impact on the overall memory footprint. So we we did a partial stack memory analysis by focusing on the seeds and commitment. And so by applying our technique on the seeds and commitment, we can see that we can reduce the footprint of these seeds and commitment from 10 to to be like few kilobytes instead of 10 or 100 kilobytes. In this slide, I will compare our work with the result from Mirith, which has a Cortex M4 implementation, and they are using also streamlining techniques. So there are only 2 parameter sets that are compatible with the Cortex M4. They partially integrates our proposed technique that we have proposed in this work, that such as the streamlining of commitment computation, meaning absorbing on the fly the commitment to complete the challenge. We know that they don't use our second technique for caching expensive commitment. And we show that their implementation can be further improved by applying our technique to save up 25 kilobytes for the fast parameter and 90 kilobytes for the level 5 parameters. So finally, let's summarize the key takeaways and future direction. So we reduced PERC memory from 1,000 kilobytes to approximately 85 kilobytes at high security levels. First constant time implementation of PERC on Cortex M4 board, covering all security parameter, and reduced the memory usage for MPC in the head signature, paving the way for them to be implemented in constrained device platform. Looking ahead, our future work involve exploring streamlining technique for new MPC in the head, a paradigm like threshold computation in the head and volley in the head. Thank you for your attention.
Thank you very much. So we have time for a quick question. So I think you can step up to the microphones in the middle of the room if you have any. Okay, I see no question. So basically, you really looked at PERC and you talked a bit about the other schemes. Did you look in details at other scheme, or you just apply what you had for PERC at other scheme directly?
Yeah, actually, what we did is more theoretical analysis on these schemes. It means that we looked at the implementation, we have measured the one that don't use they don't use heap memory, to look at their overall memory footprint, and then look at the implementation and compute what are these, what we can streamline, how our technique could be applied to that.
Thank you very much. So
Thank you.
I can thank the speaker again.
Thanks.
And so the next talk is from Mark Berlens and Matthias Kampfischer. And it's about optimized implementation for AVX2 and Cortex M4 for the scheme Mayo. So let's see what they are cooking here.
Yes, thank you very much. Let's see if this works. Okay. So me and Matthias, we're going to talk about our paper on new implementations for Mayo. I'll jump straight into the results. So what we did is we proposed new implementations for Mayo. Mayo is a multivariate signature scheme. We have implementations for x86 and Cortex M4 platforms. And the main thing we did is that we switched to a new representation of public keys. In the first specification of Mayo, we proposed to use a bit slice representation of your public keys, and we realized that that was not the best way to go. So we realized that a nibble slice representation would be more efficient. So now we propose to switch to this nibble slice representation. The reason that we are able to do this is because we use a technique called the method of the 4 Russians. This is an algorithm that was developed in other contexts, but you can use it to do matrix multiplications in small finite fields. And it turns out that for the Cortex M4, this is really better than what we were doing before. So that's what allowed us to make this switch. Okay, so I said Mayo, but what is that? So Mayo is a variant of the oil and vinegar signature scheme. Oil and vinegar is quite old. It's from 1997, and it's believed to be a very secure, well, not a secure scheme. As far as we know, it has very good signature sizes. It has very good performance. The main drawback is that the public keys are kind of large, and the reason is that a public key for oil and vinegar is a quadratic map. So you can think of it as a bunch of multivariate quadratic polynomials. And these have a property that they vanish on some secret subspace. That's the secret key. So all these polynomials are your public key, and the subspace on which they vanish is the secret key. And it turns out if you want to represent these polynomials, you just need a lot of bytes to represent it. And that's what makes the public key large. And in Mayo, we solve this problem by shrinking the dimension of this secret subspace on which your polynomials vanish. And it turns out if your polynomials have to vanish on a smaller space, it's possible to represent them much more compactly. So for example, for one of the Mayo parameters that we propose, the public keys are just 1.2 kilobytes instead of like 42 kilobytes for just oil and vinegar. Right, we cannot just reduce this space and be done, because then the oil and vinegar scheme doesn't work anymore. You have to compensate for this in some way. And the trick that we use is, so now we have these polynomials that vanish on a smaller space, but we're going to whip them up into bigger polynomials that also vanish on a bigger space, right? So we start from a map P, and somehow we construct this into a larger map, P star, that has k times more variables, but it also blows up the dimension of this space by a factor of k. And then k is just some parameter that you can pick. K needs to be big enough so that this new space that you blow up is big enough. Right, so that's in a nutshell how Mayo works. So here are some parameters, the parameters that we submitted to the first round of the NIST competition, but they will likely change a little bit when we submit to the second round. So you have 2 parameter sets for security level 1. The first one is focusing on on small public key sizes and small signatures at the same time. So this really is quite compact. So 1.2 kilobytes in public key size and 300 bytes roughly in signature size. And then the second one is focusing more on small signature size, but sacrificing on the public key size a little bit. So 5.5 kilobyte public key size and 180 bytes signature size. And then for Mayo 3 and Mayo 5, yeah, you can see the numbers here. Signature size is still quite good, and public key size is also reasonable. Okay, so before I give the numbers for the performance, I need to explain a little bit the API for Mayo. So we don't use the usual 3-part API with keygen, signing, and verification, but we break up keygen in some compact thing that output compact representations of your key. And then before you can run the signing and verification algorithms, you need to actually unpack this key and make it bigger. So yeah, but yeah, so I think hopefully this is clear. This key expansion thing, you only need to do it once, and then you can use it to sign or verify as many signatures as you want. So this gives a little bit more flexibility to the user. Okay, so here are the first numbers. So in red, we have the implementation for the bit sliced implementation, so the representation that we want to move away from. And in green, we have the new nibble sliced representation. So these numbers are a bit better. So you can see for key generation, we have more than a factor 2 speed up. And for signing and verification, we also have very nice speed up. So this is for AVX2 based implementation. Okay, if you want to compare this to other schemes, you don't want to make this distinction in 5-part API, but so you can just combine it. So this is what you get if you just add up the secret key expansion and signing, and you add up the public key expansion and verify, then you get these numbers. And yeah, so you see signing, you have more than a factor 2 speed up, and verify, you have almost a factor 3 speed up. So it's really worthwhile to switch to this new representation. And these small numbers here, just for comparison, is dilithium 2. So on the same platform, we actually are a little bit faster in signing and also faster in verification and key generation than dilithium. So yeah, that's nice. Okay, then numbers for the Cortex M4. So this is already adding up the public key expansion and verification, and public key secret key expansion and signing. Here the speed up is much less, but still we get a small speed up. And yeah, before we use this method of the 4 Russians, the nibble slice representation would be much worse. So that's why we couldn't make this switch, because we chose to like minimize the maximum. So we wanted to we went for the bit slice implementation because we thought that would be better for the Cortex M4 implementation. But with this new technique, that turned out not to be the case anymore. So we can make the switch and get this huge speed up on the AVX2 side, and at the same time get a small speed up on the Cortex M4 side. So yeah, verification, we actually don't have any speed up. Signing and key gen, we have a small speed up. And compared to dilithium now, we're a little bit slower, but yeah, not too much slower. Okay, so I give a very brief overview of how Mayo works. But if you actually start to implement this, then you'll notice that actually under the hood, almost everything is just matrix multiplication. So for example, key generation boils down to 64 matrix multiplications of matrices of size 58 by 58 by a matrix of size 58 by 8. And this is over a finite field over order 16, so a very small field. And for signing and verification, you have very similar matrix multiplication, except for signing, you also have to solve a system of linear equations. So this we do with Gaussian elimination, but yeah. So this means if you want to make an optimized implementation of Mayo, you really need to focus primarily on matrix multiplications and also a little bit on this Gaussian elimination thing. And now I'll hand over to Matthias and he'll explain how we did this.
Let me give a few more details on the implementation. So the biggest change here we did is the representation. So how we represent GF16 matrices. We kind of have 2 choices on how you order the bits in your public key. Initially, we went for the bit sliced representation because we thought this is good for arithmetic on embedded platforms. That's at least what was the case for other multivariate schemes in the past, that they use bit sliced arithmetic. And kind of the alternative to that is using the more obvious nibble slice. We call it nibble slice, like just in order of like all the 4 bits consecutive. And this is better for platforms where you have instructions that can use in-register table lookups. For example, AVX2 has shuffle instructions where you can nicely use to implement GF16 arithmetic on ARM Neon. You have similar instructions that allow you this. So we initially picked the bit slice representation because we thought Mayo is fast enough on big CPUs anyway, so we focus on the embedded case. But that meant we have a little bit slower performance on AVX2. And in this paper, we actually show that this is not necessary. We can use the nibble slice representation, and we also get good performance on embedded platforms, so we can just switch. And we also get much better performance on AVX2 and Neon. So the trick we use for that is called the method of the 4 Russians. This is a generic matrix multiplication trick that you can use in many cases. The general idea is that you you trade multiplications. So you save multiplications, but you do additions and table lookups. So let me give a few. The way you do this is you split both your matrices into very narrow strips, and then your matrix product is going to be the sum of the products of these small strips. And these strips are going to be like just depending on the parameter, but like maybe two elements wide. So you can then actually compute a table for the second matrix that contains all linear combinations of the rows of the second strip. And for this, you only need additions. And then the actual multiplication you do by looking up into this lookup table. And this obviously gives you a speed up if your multiplications are much more expensive than these additions and table lookups are. And if we look for the Cortex M4, we actually see that for the parameters used in Mayo, this actually gives you a nice speed up of like up to 2. But even if this would be the same speed, it would still be worth to do it, because on AVX2 you get a lot faster results. So like 4 to 5 times faster, because these shuffle instructions are just so much faster than using bit-slice arithmetic on AVX2. What makes this a little bit annoying here is that we're actually working on upper triangular matrices. That means you need a little bit more bookkeeping than you would need if you have just rectangular matrices. But it still turns out that overall this gives you a speed up. So, so if you then, we already had that on the slides earlier. If you plug that into Mayo, you get some speed ups, and actually the implementation we have now is a lot faster than what was existing in the literature before. And the signing at least is also much faster than what we had for the bit-sliced representation before. For verification, it doesn't matter, because there you can eliminate all of the multiplication, most of the multiplications anyway. So there it doesn't make a difference. Signing, it matters. We can also compare this to the lithium, and we see that this is actually on embedded platforms is a little bit slower than the lithium, but not crazily slower. We have some other contributions in the paper as well. So we have some new GF16 multiplication records on Intel. So for Skylake and Ice Lake, we have some speed records that may be of interest for other schemes as well. And we have proposed, or we have implemented constant time Gaussian elimination for rectangular matrices. So this is something you need in Mayo. In other schemes, you have a square matrix, and then the Gaussian elimination becomes much easier. But in Mayo, you actually need it for rectangular matrices. So this is a little bit tedious, but yeah. And there's more in the paper, so please have a look. The implementations are also open source, and you can find them linked in the paper. We have some work in progress to also implement this on ARM Neon. We're using similar techniques. That's the ones used for AVX2 in the paper. And I have put some preliminary results here on Apple M1. And it looks like my one is going to be same performance as the Lithium 2, approximately. These numbers might still change a little bit, but it's looking like Mayo is fairly comparable to the Lithium on big CPUs and a little bit slower on small CPUs. Yeah, with that, let me wrap up. So we have changed the representation. That's the biggest change in this paper. So Mayo is currently a round 1 candidate in the NIST competition. So if and when it advances to the next round, we're going to change the representation and spec and make some other small changes. And yeah, so please please have a look at Mayo, and we have some free stickers. If you need a sticker, come talk to us. And that I'd like to thank you very much for your attention.
So if you have any questions, yes, step up to the mic.
Could you comment on the change to the spec? Is it only the format of the key storage, or is there any other changes required for this to work?
For the speed ups here, the only change required is to change the order of the bits in the public key.
Can you once again say why do we get better speed up on Intel than on Cortex-M?
So because you have instructions that you can use to do the GIF16 arithmetic on this representation, on the bit slice representation, you can't use these instructions directly. You would have to reorder, but we actually had bit slice arithmetic on Intel as well. So we made this choice because we thought it's going to be faster on embedded platforms. So we knew that this is going to be worse on Intel, but with this paper now, we know that there's no point to use bit slice representation, to switch to the normal nibble sliced one, and then it's obviously faster on Intel and Neon as well.
So a kind of obvious question. So you got at least part is in the UOV submission as well, and it has two finite fields, and another one is exactly the same 4-bit field. So what would be the best arithmetic to use with UOV? Can you use the same trick?
It's the question if you can use the same trick for UOV?
For example, yes.
Yeah, so what was it again? So yeah, we thought about this. I think for UOV, you can probably only use this for keygen, if I remember correctly, and not for signing or verification. The reason is that in Mayo we have like you do matrix multiplications actually, and in UOV you only do like matrix vector multiplications. I'm simplifying a little bit, but that's like the reason. And this method of for Russian works better for
it's different shape.
Yeah, so we do a little bit more work in Mayo, so you have more opportunities to like do smart stuff. And in oil and vinegar we don't have that freedom, so we think we cannot get a really nice speed up for UOV.
Yeah, thank you.
Thank you.
Okay, no additional question. So maybe I will ask something. So the spec has to change a bit, right? Basically, you're also the team, so no issue to change it. So if you're ready to change the spec for some optimization, would you do the same for side channel issues? Like, are you ready to change the spec if you see that it gives some advantages to protect against side channel attacks? I don't know if you can talk on the behalf of the team.
I guess it depends on depends on the change you're proposing. If it means that it's gonna be a lot slower on all platforms, then maybe not. But if it's not hurting on other platforms and it's helping a lot on some platforms, then sure. Depends. You have a specific change in mind, or just in general?
In the same question.
Okay, so in general, of course, side channels are very important. We're at CHES here, so of course we care about side channels. So if there is a reasonable proposal to change something, we will consider it.
Okay, it's just that I thought that in the first part of the NIST competition, maybe people didn't care that much about the practical issues from the point of view of designer, and just happy to see that you care more about it. Thank you very much. So we can thank the speakers again. And so, yeah, I think for the next presentation, it's actually online, if I understood correctly. And sadly, I think it will not be interactive, so you'll not be able to ask questions after. So if you have some question, you can contact the authors.
Canadian visas on time. I'm sorry that I cannot present our work in person. I'm Junhao Wang, a PhD student from BNU SKPU, United International College. And this is a joint work with Alexandra Adomitai, 季彭章、望尘代、姚刘、雷斯西城、塞林盖高、东龙城。The title of our work is Revisiting Kachak and Delisim Implementations on ARMv7M. I will introduce our work from 4 parts. First, introductions. Quantum computers are being developed rapidly, and source algorithm in quantum computers will break the existing PQC in polynomial time, which will pose a serious threat to existing protocols or applications that use the traditional PQC. So this promotes the cryptography community to search for suitable alternatives to traditional PQC. So it needs to initiate a standardization project in 2016 to solicit, evaluate, and standardize the post-quantum cryptography algorithms, and announce 4 finalists in 2022. And as we can see that the latest based cryptography is the most promising alternatives in terms of security and efficiencies, according to around 4 finalists. 3 out of 4 finalists belong to LBC. And the core operations of LBC are to symmetric cryptography primitives and polynomial modifications. The symmetric cryptography primitives SHA-3, the core operation of SHA-3 is Kachak permutation, which accounts for over 70% running time, according to PQM4. And the state-of-the-art Kachak implementations on ARMv7M is based on the SKCP library by Kachak designers. And the most related work, BK 2022, studied the Kachak optimizations on ARC-16.4. However, these techniques have not been applied to ARMv7 yet. And the entity is an generalization of the classic discrete Fourier transform in finite fields. In brief, entity can reduce the time complexity of multiplying 2n degree polynomials from O(n) squared down to O(n) log n. And this work will with both Kachak and polynomial multiplication of the lithium for further multiplication potential. So the target platforms of this paper is ARMv7M, which include two platforms. The first one is ARM Cortex M4, which is NIST reference 32-bit platform for evaluating PQC in IoT scenarios. It has one high memories and 14 reusable general purpose registers. And it also has 32 floating point registers. Besides, it has some powerful inline barrel shifter operation which can merge the addition and shifting operation in one instruction. And it also has SIMD extension which can perform addition and subtraction for packed 16-bit vectors in one instruction. Most of the instructions are 1 cycles, including the multiplication instructions. And the memory access instructions are relatively expensive, which will take more than 2 cycles. Another platform is the ARM Cortex M3, which is a low resource IoT platform. It only has 14 registers with no floating point register. Similar to Cortex M4, it also has inline barrel shifter operation and relatively expensive memory access of instructions. And unlike Cortex M4, it has no SIMD extension and it has limited multiplication instructions. And one thing that should be especially noticed is that the full multiplication instructions are non-constant time, which make them insecure to use in cryptography implementation. So the Cortex constant time 32-bit multiplication is very expensive on Colin 3, which also leads to the slower 32-bit entity. So moving forward to our cache optimization on ARM-V7M. So cache computation is the cooperation of SOT3. In these standards, the cache computation involves in permute the 1600-bit cache state for 24 rounds, and each state is represented as an array of 5 times 5 lanes, where each lane is 64 bits. And cache computation is an iterative computation where each round consists of 5 consecutive operations, theta, rho, pi, chi, and eta. So we will now review the existing cache optimizations on ARM-V7M. The first one is the bit interleaving techniques. So in order to store the 1600-bit cache state on 32-bit ARM-V7M, we need 50 32-bit registers, which is not enough on ARM-V7M, and require expensive memory access to load the state. So the bit interleaving technique consists of storing bits at all positions in one 32-bit register and bits at even position in another. In this way, the 64-bit rotation can be easily handled as two separate 32-bit rotations. And another technique is the in-place processing, which means it is possible to store all processed data back into the same memory location it was loaded from. And in this way, only a single cache state needs to be stored. And the cache designer proposed a method that will return to its initial memory location after 4 rounds. And in this paper, we will focus on these two techniques and explore how to optimize these two techniques in our paper. And we also did a performance analysis to identify the time-consuming steps in cache computations. On 32-bit platforms, each round of cache computation consists of 152 XOR 50 ANDs, 50 NOTs, and 58 rotations. And on ARM-V7M, because we can combine AND and NOT in one bit BIC instruction, and we can also utilize the inline balance shifter operation to reduce the number of rotations, and we can achieve one round of the cache computation in 250 instructions. And this instruction should theoretically takes about 6,000 cycles on ARM-V7M. However, the state-of-the-art cache computations from SKCP require about 13,000 cycles, meaning that around 54% of cycles are spent in memory access. So we believe there's much optimization potential in cache on ARM-V7M. So the first technique we propose is to pipeline the memory access operation and reduce the cost of memory access. First, we noticed that the original XOR 5 macro from SKCP suffers from memory access pipeline stalls, and we managed to realize the register pressures and group fine load instruction together, which saved 3 cycles per macro code. And we also reordered some other instructions throughout the code, notably we moved the store instruction after multiple load instruction as much as possible to reduce the pipeline stalls. And secondly, we also managed to speed up the cache computation by using the lazy rotations proposed in BK 2022. So the original SKCP implementation make use of the explicit rotation for the low step through ROI instructions, which requires 47 such instructions per round. And recently, Becker and Cambridge proposed that one can omit this explicit rotation using lazy rotations, namely rotating the second operand using the inline balance shifter on arc 16-4. So inspired by BK 2022, we first utilized the inline balance shifter instruction on ARM v7m to merge the SO and rotation instructions, which also helps to reduce some cycles. And we propose two variants of CHES implementation considering the cosine effect. One has better performance but requiring larger cosines, and one has smaller cosines and acceptable performance. So moving forward to our delisting optimizations on ARM-v7m. Crystal delisting is one of 3 digital signature algorithms standardized by NIST. Its hardness is based on MLW and MSIS problems. So the polynomial locations of delisting can be operated over this polynomial ring, where the prime modulus Q is about 23-bit prime numbers. And this paper focuses on this polynomial vectors multiplication in digital delisting signature generations, namely the C times SI and C times ZTI. So the reason why we target this this operation is that the polynomial C has at most tau non-zero coefficients with 1 or -1, while the rest of coefficients are 0. And secondly, the coefficient range of SI is also very small, which is in minus eta to eta. And then we can see that the coefficients of CSI are very small, smaller than beta equal to tau 10 eta, which is smaller than 16-bit. Well, the coefficient range of TI is also quite small, which is smaller than 2 to the power of 12 or 2 to the power of 10. And the coefficients of the CTI are also smaller than beta prime, equal to tau times 2 to the power of 12 or 2 to the power of 10. So according to this beta prime is slightly bigger than 16-bit numbers. And according to CHK 21 papers, that this kind of polynomial multiplication can be treated as multiplication over the polynomial ring with a large prime modulus Q prime bigger than 2 beta or 2 beta prime. So in summary, we can use the 16-bit entity to compute CSI and 32-bit entity for CTI. So before moving to more details about our entity implementation, we need to first compare the 16-bit and 32-bit entity on contestant 3. Because contestant 3 does not have constant time formulation, which may lead to insecure 32-bit modular multiplication implementations. So, and the constant time 32-bit implementation in GKS 2020 takes a lot 6 to 8 instruction and 90 instruction for CT butterfly. So we can see that the 32-bit entity is a lot slower than the 16-bit entity. And according to SKCC23 papers, that the 16-bit entity with plantar lemmatic is at least 2 to 3 times faster than 32-bit entity. So this enable us to use the proposed CSI and CTI implementation are as follows. We use entity over 769 for CSI, similar to AHK as 2022. And as for CTI, we do not use the 32-bit entity because it is very slow on Colin M3. And instead, we propose the multi-modular entity for CTI, which utilizes two 16-bit entity to compute the CTI. With the over this prime modulus, Q prime is equal to 769 times 33 and 29. So the idea of multimodular entity to compute CTI is to use the Chinese remainder theorem to split a 32-bit entity with modulus Q0 times Q1 to two 16-bit entities with modulus Q0 and Q1. These Q0 and Q1 are very similar, or the same as Kuiper's entity, with 256 degree polynomials down to 2-degree polynomials. And the overall process of computing CT is to first perform two 16-bit entity over Q0 and Q1 for C and T respectively, then the 0.1 multiplication and invert entity. And finally, we need to use the Chinese remainder theorem to convert two 16-bit results back to 32-bit results modulus Q0 times Q1. In this way, the 32-bit entity are all implemented with the 16-bit entity on Colin M3. And for all the 16-bit entity, we can make use of the pointer arithmetic to speed up the 16-bit entity on Colin M3, according to HJJ20, our previous work. And we can see that the pointer implementations on Colin M3 is also one multiplication instruction faster than the Montgomery's. And our entity over 769 and 33 and 29 has no modular reduction in invert entity at all, which make them very efficient. And we also notice that the explicit Chinese remainder theories in computations in the multimodular entity can also be sped up with pointer arithmetic. We notice that the constant M1 is equal to Q0 invert, the inverse of Q0 mod Q1. And then we can compute M1 as in this form and speed up with the efficient pointer multiplication by a constant. So this implementation is also one multiplication faster than Montgomery's. So let's conclude our talk. So for the Kachak result, the pipeline memory access optimization results in 70 to 12% speed ups on Colin M3 and M4 respectively. And so when combined with the lazy rotation techniques, we achieve up to 24 and 21% performance boost on Colin M3 and M4. And as for the entity results on Colin M3, using our pointer arithmetic, we achieve over 4 times and 2.5 times faster than the constant 32-bit entity and variable 32-bit entity in GKS 2020. And the proposed multimodular entity also use 52% speed ups compared to the constant time 32-bit entity. And for the over CSI and CTI implementations, our CSI is 3 times faster than the GKS 2020. And our CTI, SCTI implementation is also about 20% bit faster than GKS 2020. And together with the Kachak and polynomial multiplication, we managed to improve DLSM performance by over 50%. And we also provide benchmark and hash profiling based on PQM4 for both DLSM and Kyber on CONDENSAT4, as shown in table 6. And for most DLSM variants, our Kachak optimizations use speeds up ranging from over 30%. And our Kachak optimizations helps to decrease the hashing proportion by 3 to 4%. So that's all our talk. We propose optimized Kachak and DLSM implementation on ARMv7M, and our code has been open source and merged into PQM4. And thank you very much for your lesson, and look forward to interesting discussion.
All right, so this was the last talk of the session. So next is a coffee break, but I think we are way ahead of schedule because we have no question for this one and we started a bit early. So don't be angry if there is no coffee yet. It should arrive in 15 minutes.